All right, next I guess we have James Nunez. Let me see if I can get with the program here. James works in the HPDD at Intel and spends his days monitoring, fixing, and improving Lustre testing and the Lustre test suites. Talk to him about your ideas on how to improve and expand Lustre testing. Ladies and gentlemen, James Nunez.
Hi. Let's see. Okay, so I am James Nunez, and this is not my presentation. This is work done by Ziki Tao and Gabriele, and Ziki was supposed to be here today to give this talk, and he is not able to. So I was asked to give his talk. So and Ziki did a very nice thing and put my name on the first slide. So I'm reporting on their work. So I just want to make sure I give credit where credit's due. So let's begin. So we're talking about application profiling of I/O. So this is a brief outline of what we're going to talk about. Hopefully motivate why you're interested and why we all need to be able to monitor I/O from a file system. A few things that we'll need along the way. And then we'll go into looking at some tools that Lustre provides for you to peer into the file system to see what's really going on. We'll look at a real world example, applying those tools, and then we'll clean up with a few slides, a few good things to know. So, and I should say, you know, the review committee for the talks, you know, they review the talks and give feedback. One of the feedback points was, you better talk fast, because there's a lot of slides. So, although sometimes I do talk fast, I'm not going to try to, and so if we run out of time, that's fine. The slides will be posted. But really, this first half is the important stuff, and then the second half, if we don't have time, we'll just hit a few of the points. So first of all, why should you care about your application's I/O? Well, as we all know, Lustre and many other file systems, you don't get uniform performance for any type, any size I/O that you read or write, right? And this is a depiction of that. And I should say also, I'm going to say we a lot in this talk, and I didn't do any of this work. So we means not me, but Ziki and Gabriele. So what we did here is wrote a 1 gigabyte file and using different block sizes from 512 bytes all the way up to 1 meg. And you can see this is the amount of time that took to write out that file. And as you can see, small block sizes took longer time than large block sizes. This is no surprise to anyone, but this really does impact what the bandwidth an application will get based on these block sizes. So we should be conscious of this when talking to application developers and people who want to know how to speed up their codes. So this is one reason why you should care about what we're talking about today. Also, though, so in a former life, I worked with some people that wrote applications, and inevitably I would get pulled into conversations about, hey, my application does whatever it is, 4 meg, 4K writes, and I'm seeing really poor performance. Can you help me? And inevitably, it's true that the application, you know, in general writes 4K or 4 meg writes or whatever it is, but what they neglect to tell you is, oh yeah, between every one of those writes, we go back to the beginning of the file, we update a header, you know, and we update the number of times we're writing and things like that. So check and verify. Believe your application writers, but it's always good to check and verify. So those are 2 reasons why this talk should be of interest to people, to all of us. So what are some things you want to know? I think a lot of this is obvious. You want to know how much data an application is writing. You want to know number of files, application patterns if you can get them out, number of I/O processes writing to a file. So file systems, all file systems respond very differently to, say, if you have a job that has multiple processes, multiple nodes, writing to a single file versus writing to each process writing to its individual file, those things will have dramatic differences in the way the file system responds. So these are good things to know. And throughout this talk, I'm going to help you find out how to find some of these things. So I guess one positive thing about going at the end of the conference is, I think this is the fourth time you've seen this slide, so I really don't have to say a lot. This is a depiction of what a simple Lustre configuration looks like. We have on your left, right, whatever your side, we have the management servers and metadata server. We have the object storage targets, which store your data. You can have a manager for Lustre, which is now, as you know, open sourced. And then you have, between 1 and, thousands, tens of thousands of clients. And this is, I like this, I like this depiction here. The clients are where the application runs. So just to make sure you all know that. Yeah, so most people here are aware of what Lustre does and what it looks like. So this is a very simple depiction. But I think on Brian's slides on the first day, I think he had this, second area, maybe a file system with, more advanced storage. So as our storage solutions continue to grow in complexity, more power, more moving things, more units, you really need help in insight into what the file system is doing. And Lustre helps with that. So let's look at just a slight layer below where we were. I think everything we're talking about today is client-centric. So this is a simple view of a Lustre client and what it does when it wants to do some I/O or do something to a file. You make a request to say open the file. You go through the metadata clients, which live on the client node. To the MDS, you get back extended attribute, the layout EA with a FID, and it tells you a map of your data, where to write or where to read. And then based on that, you have object storage clients on your client, and they can talk to, in parallel, the different OS servers and targets. And the method or the unit that they talk to, the clients talk to the object storage targets are RPCs. And each payload, by default, is 1 megabyte. And we all know that we can go larger now, but that's not going to factor into this talk. So let's see. So let's talk about some tools, some utilities that Lustre gives us to see what's going on in the file system. So we use very simple commands here for our sample writes, reads. So we're going to use the DD utility. So in this case, we're going to write a lot of zeros to a file system. We have 100 writes at a block size of 10 meg. When that call completes, you go look on the client. Again, we're talking about clients only right now. You use the LCTL get param, and you look at the extent stats statistics, and what you get is a distribution of extent sizes from this client. So in this case, we did 100 writes of 10 meg, and you'll see, if you look down on the extents column, these are your bins of the sizes of your extents. And you can see that the bottom one is 8 meg to 16 meg. For each read, or for reads and writes, you get number of calls in your first column, your ratios, your percentages of calls for this bin versus total calls, and then your cumulative percents, which is summation of your ratios. So in this case, again, we did 100 writes, 10 meg, and we see that it does show up in the 8 meg to 16 meg bin. 100 writes, and that's all the writes that we did. So that's how you read extent stats. Now, you probably want to iterate on this on getting the statistics. So you need to know how to clear out the statistics. And one way to do that is writing using setParam to, you can actually echo something into the extent stats file, or you can set it to 1, and that will reset all of your counters. And again, just another example, a single count writing a gig, and you'll see, again, in the extent stats, we see 1 call, and that's 100% of your writes. Excuse me. I see time fleeting. So that's great. That's a single call. You know, these are artificial examples. So let's try to get a little more to a real application. So let's run 3 DD calls, all writing the same number of write calls, or doing the same number of writes, but at different sizes. And we put those in the background. They run simultaneously, and then we look at our extent stats, which has been zeroed out, which has been reset. And we look and we see that, in fact, we can see that for each of the write sizes, 1 meg, 128K, and 31K, that we actually, each of the calls are in the correct bins, number of calls 1024 each, and the ratio, since we have 3 processes, each writing the same amount of data, or same number of calls, they're each a third of the totals, and then your cumulative totals. So this is great, and this is an artificial example, which works out really nicely, but what happens if you had lots of different processes writing different sizes, maybe the same size? It'd be very hard to understand who is doing what in this extent stats statistics. So how do we figure out which process is generating what IOs? And so let's do the same experiment. We're going to zero everything out. Again, kick off 3 DDs. In the background, we get the PID, process ID. And then, so Lustre, the great minds who wrote Lustre thought about this, and so we're going to look at something else, LCTL, get param, extent stats per process. And this is essentially the extent stats data for each PID. And as we can see from the example, each PID is broken out, and the correct binning, or the correct number of writes, is in each of those process IDs. So this is a single file, but it's divided up like it's 3 different extent stats calls. So that helps to differentiate what process is doing what writing. So let's change gears just a little bit. So that's extents on the OSTs. Now, since the network can impact your bandwidth or how you write things, again, we have some statistics or utility to look at what RPC stats. So let's write, again, using DD, write out a file to our file system. We'll do a lot of whatever, 8K small writes, 128K writes. Look at the RPC stats, and we actually see that we get 200, RPC stats. It has a variety of statistics in that file. One of those statistics are the pages per RPC. Again, this is a histogram or a histogram of the RPCs that are pages per RPC. And so on a 4K machine, which we had, we wrote out 256 pages per RPC. We did 1024 of them. Now, you might say that doesn't jive with what you did. You wrote 8K, 128 K bytes or writes. True, but so this is the RPC stats is a true depiction of what Lustre is doing for you. And so this actually gives you a lot of insight. So Lustre can aggregate small IOs together into a single RPC, and that's what's happening here. And again, you may or may not know that, but for those who don't, you can check the RPC stats and get that information. So this is all very helpful. If you want to stop that for some reason, this is just an example of, we're using the sync flag on DD, and it shows that we're actually doing 1024 writes of 100K, and that's represented in that bottom, the distribution, 32 pages, 1024 RPCs. So there's a couple of things I should tell you. So the RPC stats, they're associated with an OST. So if you look at the get param, you'll see it's in the OSC category in the proc files. And you get the file system name, and then it's an OST number. So you get RPCs going to each of the OSTs. And if you wanted all of them, you could just do, put a star there, wildcards. Get param and set param will take wildcards. So for this example, and in general, you may want to constrain, since if you have a large system, a lot of OSTs, it may be hard to know where you're writing, what your application is writing to. So if you are able to play around with the application, and in this we had an artificial application, so we could play around, and so what we did is we actually constrained the writes to a single OST. We did that using pools. There's some information on how that was done. You can also do like set the stripe for a directory and write into a single directory to focus where your writes go. So, the rest of this talk is about applying those statistics to a real application. And I'm going to go a little bit quickly over this. So what we use is the NEMO modeling framework. So NEMO is the nucleus for European modeling of the ocean, and it is a state-of-the-art test framework for different modeling engines. So a few of those engines would be, like ocean water, sea ice, things like that. And so this application really is a black box to me and to perhaps others. So we're going to try to use those tools to see what it's doing. And again, in the interest of time, I'm going to go a little bit quickly through some of these things. Might gloss over some of the details. But so the goal here is take this application, which we may or may not know anything about, try to analyze what it's doing, for I/O, what it's doing on the file system, and then ultimately the goal usually for this stuff, for an I/O analysis, is to make an application run faster. Sometimes it's though to understand an application. And so we have a really constrained system here, a couple compute nodes using Omnipath for the network and using SATA SSDs for the servers. Let's see, so we're going to artificially constrain where the application writes to. This may or may not be realistic. This may or may not be how people run the application, but we're just doing this for us. We're trying to understand the I/O patterns, so you can do some artificial things if it still preserves really the way the application works. This may give you horrible performance, but at this point, that's not the goal. The goal is understanding what the application is doing. So reset all the counters. We're using K&L nodes. We'll look at CPU utilization, things like that. So for people who know or understand NEMO, this is how we ran it. So let's see. So let's, we introduced the three statistics for reasons. So let's look at extent stats first. So we kick off NEMO with that call. And after, a few minutes, we try to look at the extent stats and try to see what's happening. And we see a lot of I/O is happening, a lot of read going on, some writes. It's kind of all over the map. And it's, if you ask me, well, how do I optimize this? I'd say, I really don't know. Can we start over? So, but that's fine because applications go through different phases. Usually start up, they read a lot of files to get in variables or load libraries or whatever they need to do. So one of the nice things here is let's let the application run for a couple minutes, try to see if there's a clear pattern. There may or may not be. In this case, there's not. So let's reset all these stats, the extent stats, and let's see what's happening. And so we reset, wait a few minutes, make sure that some I/O is done, because that's what we're measuring. And we start to see a pattern emerge, or at least some clustering emerge, right? We see that there's about 80%, a large percentage of the reads are small, 0 to 4K, and a large percentage of the writes are, large in quotes, depending on who you are. That's large or not, 4 meg to 8 meg, and 79% of the writes are there. So this is positive that there's a pattern emerging, and maybe we can do something with that pattern. So that's helpful. We want to know who is doing the writing, what process is doing the writing, and again, using the extent stats per process, we're actually able to figure out that there's one guy doing the reading and the writing here, this PID. And so we look down, however you find your PIDs and what they're doing, PS here. We find out there's a single, this NemoPar exe executable that's doing a lot of the reading, writing. We look at CPU usage and see that we have some high usage, for that guy. Let's see. I'm going to jump over here. So now let's see what RPC stats tells us. We see that there's, for the reads, a high percentage of the RPCs are small, which seems to correlate with our small reads that we saw with the extent stats. So that's very positive. So we see there's some 4K IOs. So after we reset the counter, again, we don't see those small reads anymore. If you recall, when we were looking at the extent stats, we ran, saw some 4K reads, cleared the counters, saw 4K reads again, and since I know this, cleared the counters again, saw 4K reads, but we don't see that in the RPC stats. And so you might think at first things are broken, but these reporting structures are pretty good, and what this is showing you is actually there's not RPCs going to the clients for reads. A lot of these reads, or in this case, all of these reads have been cached by the Lustre client. So that's very positive for us, because then we don't have to try to balance a read and a write workload. And so just to be good, to be smart about this, you run this application several times, you do this a few times, look at the different stats at different times, and the pattern will become clear to you. So again, large number of small reads, and we get a large number of large, in quotes, writes. So what have we learned from this profiling exercise? We were able to determine that a lot of the reads, most of the reads, after a certain time were cached, and we had a fairly consistent write size. Therefore, we could optimize for the writes and not be so concerned with the reads. So you may say, if you're awake and didn't crawl too much last night, you might say, hey James, that's great. I've tried to use extent stats before, and you need to be root to clear out the counters. And I think that's true. And that does hinder some things, but with just a little bit of math, you can actually figure out, as a user, you can actually figure out what's going on. You can use these statistics. And the way to do that is, all these statistics, if somebody doesn't reset the counters, they're cumulative. And so you can run the extent stats in this case, see the number of RPC calls, run your application, run RPC stats, run RPC stats again, and then you can just try to figure out, okay, I have a snapshot time, when before my application, after my application, subtract one from the other, you get your elapsed time, and you can see the RPCs, the writes. You can get the number of writes for your application based on, again, subtracting those two values. So it's maybe not as easy or as straightforward, but you can still use this being just a non-root user. So in summary, I'll summarize my very short talk. So Lustre gives some great statistics. If you are not aware of these, if you haven't used them, it's a good thing to gain insight into what an application is doing. And sometimes, things like the RPC stats, you don't know what Lustre is doing on your behalf. Some optimizations, and if you don't like those optimizations, you may say what Lustre is doing to me, and you can actually work to turn that off. So it's just good to have that knowledge. And again, if you're helping application developers or people who've been writing applications for a long time, this, again, is very helpful. Applications would be a black box. So I think that's all. And so I want to say 5 minutes to read the notices and disclaimers to you. But I think you can all read this. I think I won't do that for you. So I'll take any questions. And thank you very much, and thanks to Ziki and Gabriele for doing this work. So. There's a question down here.
Hello, James.
Hello.
I do not have a question, I have a comment. So what I used to trace this was to use a block trace with SystemTap. I gave a demo to James Nunez yesterday. So what you did was excellent. So I use block trace, get a lot of information, use awk and grep to derive. I didn't know about this. I didn't know what Dimitri showed of the frame graphs. So I was tracking the IOs from client to staging, which is OSS, and then from the request queues to OST, etc., those kind of a thing. So I might be having those scripts. So if you want it, you can I'll share it with you in case this helps. I don't have a question for this. There are many things which is from the top level, but what I was doing was to actually see the individual BIOS which are flowing from client to the OST.
Okay. Thank you for the comment, Arshad. And I'm having a hard time hearing for some reason, so thank you. But yes, there are alternative methods to get similar information, I think was your comment.
So instead of looking just from the read-writes perspective, I was looking at the individual bio, which was actually flowing using block trace and SystemTap. So I have scripts for that. We can still do the same thing. We have to do a lot of awk and grep to actually filter out information. But it's an interesting path to follow.
Okay, thanks. Yeah,
I'll share the scripts with you.
Make those scripts available to all of us. John.
Hey, James. So I do have a question. I like how you showed how to do the profiling if you're not root. How much profiling can you do if you don't have a dedicated service time where your app is running in isolation?
Yeah, that's a good question, and I apologize if I haven't made that clear. So this is on this is client-centric. So if you have the client alone, then you can see a lot, right? So you can see the RPCs and you can see the extent stats. If you're not alone on the client, you can get your process ID and you can see the extent stats. The RPCs, if there's other people sharing your node, I don't know of a way to isolate yours. So there is some, if you got the node, then you can do all of this. And I guess that's a nice thing about these stats, right? The file system can be very busy since we rarely have the luxury of kicking everybody off the file system to run our app. So yeah. So Oleg had a comment that I can't hear. What? No, I can't. So
you can't hear.
He's going to.
You probably could use job IDs to isolate RPCs that are interesting for you. And then the servers will actually split them out in the relevant job ID statistics.
Okay. I cannot correct Oleg even if I wanted to. So. Anything else? Any other questions? One back there.
So this was really interesting, but I just checked that on Lustre 2.5 version I'm using now, by default the statistics are disabled. Is there any impact on the system, performance maybe?
Great. So thank you for reminding me of something I should have said earlier. Yes, by default, the extent stats per process, and one of the other stats are turned off by default. And that's because there is overhead in collecting or monitoring these, to collect the statistics. I personally can't tell you how much, 1%, 0.5%, 50%. I don't have that calculation, but they're turned off by default, and to turn them on, you just have to set them to any value or echo into the file anything other than 0 or disable or something like that.
Yeah. I was just thinking if it's possible, to enable it by default and maybe store all those statistics in some kind of database and provide web service for end users where they can just tracking the job ID check, okay, this is IO pattern on my application, but.
Sure, yeah.
But it has performance impact, yeah, so.
The statistics are available for you, right? And that's the beauty of this, right? You can turn them on, you can turn them off, you can log them to a database. I mean, yeah, if the overhead is acceptable to you and the information is helpful to others, or to you, yeah, go for it. That's the beauty here, right? These statistics are provided to you. Do whatever you will.
Thank you.
Sure. There's another question over here.
Is it possible for a non-root user to turn those stats on and off?
That's a good question. I don't think so, but I'll appear to, Andreas, no. It's not able to. So you'll have to get friendly with the system administrator. Just get friendly with him once, and then, that's right. I've gone over time. Is there anything else? If there's anything else, please talk to me. I'm happy to talk about this to you. Thanks.